All right, today I'm going to do the examples of the work, power, and efficiency worksheet. We'll start with number one. Number one says calculate the work done. So work is my unknown by a 47-pound force. So my force is 47 pounds. Sorry, pushing a pencil a distance of 1.5 feet. Work is equal to force times distance. They must be parallel. They don't say different, so we're going to assume these are parallel. Okay. And so when we solve this, you just plug these in. So it's just 47 pounds times the 1.5 feet. And then we multiply that out, we get 70.5 foot-pounds. That's all there is to that one. Number two is very similar, but it's a little more involved. It says calculate the work done by a 47 Newton force. So the work, again, is my unknown. My force now, we are in the metric system because we're 47 newtons. Pushing a 0.25 kilogram pencil, so my mass is equal to 0.025 kilograms. And then my distance is equal to 0.25 meters. And then against a force, that's equal to 23 newtons. Okay, so this is basically the force applied, and this is the force really with something we call friction, right? Whenever you push on something, it slides, we have friction. So if we want to look at the overall work done, we have to look at the overall force. And so we have this force applied that's pushing this way of 47 newtons, and then we have the force of friction pushing back with 23 newtons. And so then my force net, my overall force, is just going to be the 47 minus the 23 because it's going the opposite direction. And so my overall force is going to be 24 newtons. Okay, so now when we do this problem, I say work is force times distance. We didn't even need this. That was just unnecessary information, but that's okay. But now my force is equal to the 24 newtons, okay, times my distance of 0.25 meters. And when we do all that, we end up with 6. And when we multiply the newtons times the meters, we end up with 6 joules. A Newton meter is a joule in the metric system. All right. We could find the work done by just the 47 pounds or the work done by the 23 newtons, or the 23 newtons. So we'd have the work done by the applied force or the work done by friction, but we just solved for the net work. They didn't really say. This is sometimes just the hard part in physics. What are they trying to get? Okay, so this next one says if a small motor does 520 joules of work, so now we know the work is 520 joules. To move a toy car 260 meters, so my distance is equal to 260 meters. That's a lot. What force are we looking for? We have the same equation. Work equals force times distance. Okay, but now we're solving for force, so we're going to get rid of the distance from each side. And we get that my force is equal to work divided by distance. And so we can plug our numbers in there. 520 joules over 260 meters. And when we do all that, they made it nice for us. We end up with 2 newtons. Okay. Number 4. Number 4 says, where's my stuff here? A power mower does 9.00 times 10 to the 5th joules of work. So my work is equal to 9.00 times 10 to the 5th joules in 0.5 hours. So my time is equal to 0.500 seconds. Oh, hours, sorry. Hours. What power does it develop? So power is my unknown. So let's jump. So there's my givens. Okay, this is the same as if you wanted to write it out, you really don't have to. We're going to move 5 decimals, right? Joules. And then hours, we don't like hours. We always have to go to seconds. Seconds is our base unit. So half an hour is 30 minutes, right? And 30 minutes, every minute is 60 seconds. So we're going to be, this is equal to 30 minutes. We could do that little conversion, right? We could have done that with the hours too, but I kind of knew that one, so I didn't do all this. So we're going to put minutes down here, okay? And then we're going to put seconds up here. For every 1 minute, there are 60 seconds. That's my equality. So 60 times 30 should be 800. 1800, I'm sorry. Did I say 800? 1800. That's why I have calculators to save me. 1800, the minutes go away, and now we have seconds. Now we've converted that. We have straight joules, straight seconds, and we're looking for power. Power is equal to work divided by time. Well, look, I have work and time, nothing to rearrange. My work was 900,000 joules. My time was 1800 seconds. Okay, so if we take that, 5 zeros, and we divide it by 1800. I forgot to put the divide symbol. We end up with 500. We're going to have joules over seconds, which we wrote down in our notes, become watts. So let's do that one. Okay, 5 says how long would it take a 500 watt electric motor to do 1.50 times 10 to the 5th joules of work? Okay, so now we have that my power is equal to 500 watts. We're doing 1.50, so work is 1.50 times 10 to the 5th joules of work. And they said how long, so my time is my unknown. So it's really the same equation we had before. We can rewrite this if you like. You don't have to do this. But if it makes more sense for you to have it out of that scientific notation, you can put it in your calculator with scientific notation as well. So power is work divided by time, but we're looking for time, so we're going to multiply both sides by time to get it up to the top. And we'll have that time times power is equal to work, because it went way over here. Now we're going to divide both sides by power, so we end up with that time is equal to work divided by power. Okay, so time is equal to the work, which was the 150,123 joules, and power was 500 watts. Okay, if you want to put this in as the exponent, it's 1.5, and then you do this little EE, so you do second E, and then we did to the 5th power. And we're going to divide that by the 500, so we can see that that's the same as, so it doesn't matter which way you do it, oops, you get the same thing. So whether you put the little E, it's EE right here, so it's second and that comma, and you get that little E. So if you want to convert it, you can. If not, it doesn't matter. And we get 300 seconds, right? Because watts are joules per second, so we have joules over joules per second. And so these invert, and we have 1 over 1 over second, which ends up being just seconds. And so we get that thing. Okay. So let's move on to 6. How much work can a 400 horsepower car engine do in 60 seconds? I'm running out of space. Let's go to the next page. Okay, so how much work? So work is my unknown. Can a 400, so my power is 400 horsepower, do in 60 seconds, so my time is equal to 60 seconds. If it's 100% efficient, so my efficiency, this funny looking in thing, is 100%. That just means that the power in equals the power out, which means we don't have to do anything, right? Whatever power we have is the power we have. It didn't change throughout. If it was some other difference, the power out, if it was 80% and the power was 400 and it was only 80%, then we take 80% of that 400 and have 320 horsepower out. Okay, but it doesn't matter in this one because it's 100%. The other problem we have here is this is in horsepower. We need power either in watts or we need it in foot-pounds per second. Okay, so 1 horsepower is equal to 550 foot-pounds per second, or 1 horsepower equals 760 watts. Okay, so you can decide and you can convert either way to get it into foot-pounds per second or into watts. So if we convert our power, okay, so we're going to take our power, it's 400 horsepower. And if I do a little doodad here, if we put horsepower on the bottom, then we could put foot-pounds per second up here on the top. So 550 and 1. So if we multiply this, we end with 220,000, right? The horsepower went away, and so we just end up with foot-pounds per second. Or we can convert our power into watts, and we can say that 400 horsepower. And again, we're going to have 1 horsepower is 760 watts. And when you multiply that, we get 400 times 760. We get 304,000. I'm sorry. This is 746. I wrote that down wrong. I'm looking at it here on my thing. I don't know why I wrote so. So let's try that again. 400 times 746. It's 298. I did this one right. 298,400 watts because the horsepower goes away. So there's my power. So now we got to go back to the original thing. We were looking for work, right? So power equals work divided by time. If we multiply both sides by time, oops, it goes away. And we end up with work is equal to power times time. So now it's going to be equal to the 220,000 foot-pounds per second. We can multiply that by the 60 seconds. Or work equals power times time, and we can do our power as 298,400 watts times 60 seconds. And so we get 2 different answers depending on what we did. Okay, so if we take 298,400 times 60, we get 179,04123. What is that? 17,904,000. And it's work. And so in this case, it'll be joules if we're in the metric system. Okay, so we can do it that way. If we want to find it in the foot pounds, we take the 220,000 and we multiply it by the 60, and we get 13,200,000 foot-pounds. Either one is correct. Okay, let's move on to number 7. All right, so on number 7, it says a man pushes a car using an average horizontal force of 500 newtons. So my force is equal to 500 newtons to move at 500 meters. So my distance is 500 meters. How much work does he do? So work is my unknown. Work is force times distance. I think we're parallel there. We're going to assume parallel. So that's just 500 newtons times 500 meters. And so we should end up with 500 times 500. And we end up with 250,000. And newtons times meters just ends up as joules. So that was part A. So on part B, it says how if it takes him 30 minutes, so now my time is equal to 30 minutes, but we need that in seconds. So my time is equal to, if we convert that 30 minutes, in 1 minute, there are 60 seconds. So 30 times 60 is 1,800 seconds. So my time is 1,800 seconds. Okay, so we can do our conversion. What was his power? So now this case is power. Power is equal to work divided by time. We'll just solve for his work, and now we converted for his time. So it's 250,000 joules over 1,800 seconds. So divide this by 1,800. And we end up getting that we have 138.9. We round that off. 138.9. And we're looking at power, and we have joules per second, so that ends up being watts. Okay, and then part C says if he forgot to take off the parking brake but used the same amount of force to push the car the same distance, how much work did he do? Okay, well, if he used the same force and the same distance as he did back here, force times distance, we get the same thing. So it's the same as A. It did not change, but it's still equal to the 250,000 joules of work. Nothing changed. Okay, let's go on to number 8. Number 8 says how many joules of work is done by a 40-watt light bulb in 60 seconds. So we're looking for joules and work. So that's my unknown. It says my power is equal to 40 watts. This says my time is equal to 60 seconds. So power equals work divided by time. If we multiply both sides by time, we get that work is equal to power times time. Power is 40 watts. Time is 60 seconds. 40 times 60 should be 2,400. Yeah, so we end up with 2,400 joules. And that's all there is to 8. Okay, let's look at number 9. Number 9 says a 15 Newton weight, so that's my force. 15 newtons, a weight. Remember, anything in newtons is always a force. It's raised 10 meters in 7 seconds. So my distance is equal to 10 meters. My time is equal to 7 seconds. And it says, what is my power? So we know that power equals work divided by time. They didn't give us the work, but we know work is equal to force times distance. So we can do two different problems. We can multiply the force by distance and then take this work and plug it in up there, or we could just say power is equal to force times distance over time. So all I'm doing is substituting this W in up here. I'm going to take the FD and put it up there. So it just kind of saves me a step. So my force is 15 newtons, my distance is 10 meters, and my time is 7 seconds. And so now as we multiply all those out, we have 15 times 10 divided by 7. We end up with 21.428 or 21.43. We're looking at power, so it's watts, because newtons times meters is joules. Joules over seconds is equal to watts. And finally, our last one, number 10. Number 10's got a lot of parts to it. So we have a 100-watt light bulb. So that's my power of the, we'll just call it LB of the light bulb to keep track. Okay, is 100 watts. It was turned on for 2 hours, so my time is equal to 2 hours. We're going to have to convert that into seconds. We might as well do that now. So we have 2 hours. There's 60 minutes in 1 hour. And then there are 60 seconds in 1 minute. So the minutes will cancel, the hours will cancel, and we'll end up in seconds. And we'll end up with that is 7,200 seconds. So that is my time. To produce the same amount of energy, how many kilometers would you need to raise a bucket of water? So my distance is my unknown, and we're going to want that in kilometers when we're done. The bucket of water is 45 newtons, so my force is equal to 45 newtons, which is just over a gallon of water. Okay, we're going to assume that there's 100% efficiency, so that means my power out and my power in are the same. So the power that the light bulb has is the same amount of power that I mechanically have as I'm raising the bucket. Okay, so first I have to solve for work in order to solve for the distance. So this is kind of where we need to see the things, because we know that we're doing work, power, and efficiency. We know down here that we have work equals force times distance. Okay, so my distance is going to be work divided by force. I have the force, I need the work. So, but I also know from up here that power equals work divided by time, and so that work is equal to power times time. So I'm going to use this equation and this equation. It's an awful W. These two equations to help me solve for that distance. So first, let me solve this guy up here. Okay, so we can say that work is equal to power, which was the 100 watts, times the time, which I solved for, which is 7,200 seconds. And so when I do that, we just put 2 more zeros on it, and we get 7,200 with the 2 zeros, so 720,000. And so we end up with joules. So that's my work. And then if I go down here to distance, I'm going to get distance is equal to that work that I just solved for. I could have combined these two like I did earlier. Okay, it's joules over my force of 45 newtons. And we get 720,123 divided by, what was it, 45? We end up with 16,000. Oops, over here. 16,000 meters, but they asked in kilometers. Okay, so now we do have to do the conversion. So 16,000 meters. For every 1 kilometer, there's 1,000 meters. Okay, we can get that from our conversion sheet. And so when we multiply this through, we're going to have 16,000 over 1,000. 1,000, and we end up with 16. The meters went away, and we ended up with kilometers. All right, let's look at part A. Part A says the mechanical to electrical energy conversion is 20% efficient. What is the distance required? So now we know my efficiency is 20%. We got to figure out what our mechanical and electrical energy was, right? The energy, the power that we had was from the light bulb, from the electricity, was 100 watts. So the power was 100 watts. We got to figure out, is that the in or the out? Okay, so it's mechanical to electrical. So the electrical is the out. Okay, the power in is what I want. Okay, so we got to solve for that power in, so then we can redo that distance equation that we just did in order to solve for the distance using the work equation. So we got to solve for this. So my equation says that efficiency, excuse me, is equal to the power in, sorry, it's equal to the power out, right? We have our thing over here, efficiency is equal to power out over power in times 100%. Power out over power in times that 100%. Okay, so this up here, this is the electrical, and then this is the mechanical. Power in, right, mechanical, power out, electrical. We want to know what's power in. So first let's get him off the bottom. So we're going to multiply both sides by power in. We'll get him off there. So we'll say the power in times the efficiency is equal to power out times that 100%. Okay, we want the power in, so we're going to divide now by the efficiency. So we're going to divide this side by the efficiency. And we end up with that the power in is equal to the power out times 100% over the efficiency. And now we can solve all that, because the power output was the 100 watts. We have 100% over here. And then the efficiency was the 20% that they told us in the problem. And so now if we do all that, we're going to have 100 times 100, try it again, divided by 20, because right, the percentages go away. And we end up with 500 watts is what we have. So the power in is 500 watts. Oops, I get rid of this so we can see better. All right, now it says, what is the distance required? So we're basically going back and doing the exact same thing. So if we go back and look at what I had here, we're still solving for this distance just like we did before. So we're going to take our power and we're going to take all this. So we really need all of that information again. Okay, but now we know our power is 500 watts. So now our power is 500 watts. My time, my converted, is still the 7,200 seconds. My force is still the 45 newtons. Oops, put this up where you can see it. And then my distance is still my unknown. And again, remember, we want that in kilometers. Okay, so our equation, we're first looking for, we got to look for the power, just like we did before. Just like we did, get all this on the screen. Power is work over time. Okay, but we're solving that for work. So we can say that work equals power times time. So now it's going to be 500 watts times my 7,200 seconds. Okay, so 500 times the 7,200. Now we get 3,600,000. Okay, so that's going to be in joules. So that's my work, and then we're going to use that work equation to solve for distance, and say that distance is work divided by force. All right, we did all this before, so we don't have to rearrange again. And now we know our work is 3,600,000 joules. My force is still 45 newtons. And so now we're going to divide. Just have to keep all this in the screen. 3,600 newtons, we're going to divide that by 45. And we get 80,000. So my distance is now 80,000 meters. Remember, they want it in kilometers. We know that there's 1,000, so really the easiest part about metric is we can just move it 3 places and we end up with 80 kilometers. You could do that conversion like we did before, right? But you see, we just moved our decimal 3 places, and so we end up with 80 kilometers. Okay, Hopefully that makes sense. Let me straighten everybody back out here again. And let's look at part B. In part B, everything down here, part B says if you traveled around a circle 1 meter in diameter, okay, so we're going to go around this circle, and we know the diameter across the middle here is equal to 1 meter. How many total revolutions would you make? Okay, so it's kind of like we're winding this thing up around a bucket. So how many revolutions we would make if we're using this 80 kilometers thing that we have. Okay, so if we know the circumference of the circle, right, if the diameter is 1 meter, how far is it all the way around? Because that's how far the rope is going to go for each revolution. So the circumference, right, if we do that, that's, we have to think back, what was circumference? It was pi times diameter, right? 2 pi r. We don't have the radius, we have the diameter, so that's the same as, sorry, pi times diameter. So that's the circumference. We want to know how far around that thing is. Okay, the diameter is just 1. Okay, so that kind of just goes away. And we can just say that we have our revolutions, how many times we have to revolve, is we have to take our 80,000 meters that we solved for over our pi times our distance of 1 meter. And that'll tell me how many times to go around, right? Because that's the distance of 1 time around. How many times total do we have to go around? So we take our 80,000 and we basically are just dividing that by pi. And we end up with this crazy number, 25,465. We'll round it up to a whole number here. 25,465 revolutions. Right, so the meters went away. Whew. Okay, so now we're on to part C finally. It says the bulb stayed on for 4 hours and required 2 megajoules of mechanical energy to produce the light. What is the efficiency? Okay, so now again we have to go back and look at the efficiency. Okay, so we're looking at our power. So we got to figure out our mechanical power. Okay, so there's 2 megajoules of mechanical energy. That's the energy, but we have to look at power, and we have 4 hours. So our time is equal to 4 hours. We have to convert that into seconds, and then we have 2 megajoules is equal to our energy, or our work is equal to 2 megajoules. We can convert this easy. This is just 2 million because mega means million. This one up here, we just take our 4 hours. Right, there's 60 minutes in 1 hour. And then there are 60 seconds in 1 minute. So the minutes go away, the hours go away. We have 4 times 60 times 60, which 4 times 60 times 60. Oops, missed the times button. Let me try this again. Slow down. 4 times 60 times 60. Bam. We get 14,400 seconds. Okay, so now we can look for the power, the mechanical power. Okay, so we have to find that mechanical power in order to find the efficiency, because we need power in and power out. Okay, so my mechanical power is equal to the work over time. So it's the 2 million joules that I have over the time of 14,400 seconds. 1, 2, 3, 4, 5, 6 divided by what I just got. And I get 138.9 watts. Okay, so that, remember, mechanical was the input power. So my equation for efficiency was equal to my power out over my power in. Remember the out, okay, the out was the light bulb, so the electrical. Okay, and the input, this was the mechanical. Okay, so that's what we just solved for, and the electrical we had way back up there was 100, and this is all times 100%. So the power out, the electrical, was the 100 watts that we got at the very beginning of the problem. The power in that we just solved for, the mechanical, was 138.9 watts. And then we're going to multiply that, of course, by the times 100 to get it into percentage. So now we have 100 divided by 138.9. 71.9, and then multiply that times 100 to get percent. And we have 71.99. Let's just make that 72%. So it's 72% efficient. That was fun, wasn't it? All right, have fun.